this is Maker Tutors. Here we'll be proceeding on our topic theory of structure on simply supported beam with uniformly distributed load UDL using double integration method. So in the last lesson I've solved for simply supported load with point load using double integration method. Then here we'll be doing for UDL. So here is the diagram. The load is uniformly distributed. That means it's having equal load. The load distributed over the span of the beam. So we are having x at a distance from point B. Then we're having the weight or the load in units per length. Then we are having the slope. The slope can represent as theta A or IA anyway. So we are having the length. Total length is L. Then when you want to change the UDL, the load is spread across all the span of the beam. When you want to change it to point load, it appears at the center. So the distance will be at point C, that will be L over 2, making total of L. So these are the reaction for WL over 2. So reaction at A equals reaction at B, WL over 2. So here guys, let's go into business. Maximum bending moment is equal to this WLX over 2. That means the reaction RA or RB, either RA or RB, WL over 2 times the distance x minus WX squared over 2. So the positive sign in this equation is also showing the sagging. The positive for sagging is always positive, then hugging is negative. Hugging is something like this. So hugging is negative. So from equation of bending moments, from this equation we substitute any place you see mx, we put this EI times the deflection. So we proceed. So when you input it, though I skipped some steps here. When you input it, you resolve it, then you do your first integration. When you integrate, you have this EI integral the square y over dx square, then blah blah blah, equation 1. Then integrating, when you integrate it, you resolve it to be this. So follow the steps that will be simplified for better understanding. Follow it, then you get the first constant of integration C1. So this is equation 2. Don't forget equation 1, equation 2. So when x is equal to L over 2, then divide the x is 0. When we assume that x is from here to here, but when x is equal to this distance from point B to the midpoint, that's L over 2. So we come back here, then divide the x is 0 at that point. So we input the value to get our constant. So that will be simplified for better understanding. So we get our constants for the condition of the boundary to be what? This. as you can see, minus WL cube over 24. So after getting your constant, the next step is substituting that's your constant of integration into the previous equation, that's equation 2. So you substitute it into equation 2, then you resolve it to be this. You can see, then call it equation 3. So note, maximum slope occurs at A and B. Maximum slope occurs at A and B, both A and B. The slope at A is the same thing as the slope at B. So here guys, so here we substitute x to be equals to 0. That means x at A and B at this point, x at B, x will be 0, at A, x will be 0. So substitute it. Then I told you that this is divide x equals the slope equals theta, or you represent with this, then you will resolve it with this. So the slope, the angle of the slope is what? Minus WL cube over 24 EI. And that's for the slope. Then by symmetrically, when you divide it into 2, what you get for the slope of B is the same thing as what you get for A. So that's what this is all about. So then after getting the slope, the next thing is we integrate and get for maximum deflection. So second integration, proceed from the previous equation, equation 3, you integrate it, follow the steps, integrate it, then when you integrate the y, the x becomes y. When you integrate this, you have this. When you integrate this, you bring out the coefficients, that's 1/6. Then when you use your integral equation, you resolve it to be this. So then we get our equation 4. So when x, so we want to get the value of C2, we want to eliminate the value of C2. So when x is 0, y is 0, so C2 will be what? 0. So when you substitute C2 into the equation, so C2 is off, so we get equation 5. So maximum deflection is at midpoint. Maximum deflection of a simply supported beam is always at the midpoint. So here, maximum deflection, substitute x equals L over 2 in equation 5. So when you substitute x equals L over 2 into the equation 5, you resolve it as this. So we get maximum deflection for simply supported beam using UDL as this. So the negative sign is showing downward deflection, that is deflecting downward. So that will be all for today, guys. So here, note also slope and deflection will also be expressed in terms of total load. That means W, that's capital W equals WL. So this formula can be, the formula we derive for slope and deflection can be written as this. So Thank you. In the next class, we're talking about cantilever with point load at free end using double integration method to resolve slope and deflection of beams.